This is the last of a three-part series looking at allostery and cooperativity. In the first video, we looked at the mechanistic origins of allostery. In the second video, we looked at some cool biochemical examples and biological examples of allostery. And in this video, we're going to look at cooperativity, which is a extension of allostery applied to multiple sites. So let's get into it. So we're going to be talking for at least part of this video about hemoglobin, which is maybe the example par excellence of cooperativity. If you look at our red blood cells, they are absolutely packed with hemoglobin. The iron in the hemoglobin is what gives them their red color. And as you probably are aware, the point or the purpose of a red blood cell in large part is to transport oxygen from your lungs to your working tissues, to your muscles, for example. And it's doing so using hemoglobin as the oxygen carrier. Now, hemoglobin operates as a 4 subunit protein. So it's got 4 different protein chains that are glued together into a quaternary structure. These things are responsible for taking the oxygen in the lungs and dropping it in the, say, muscles. But it raises the question, why? Why do we have 4 chains in a tetramer instead of just, say, 1 chain? Why can't we just have a single chain of hemoglobin that's floating around doing this job? And we know, for example, that individual subunits of hemoglobin can bind to oxygen. So it's made out of 4 globin proteins glued together. There are versions of globin proteins that exist as individual subunits, as monomers, and they bind happily to oxygen. I'm actually showing here the example of myoglobin, which I'll talk more about in the next slide. But myoglobin binds to oxygen via a heme, which is this shown here in this structure, and then it's shown chemically over here. And basically oxygen will sit and interact very favorably with an iron that is inside of the heme ring, as well as some coordinating residues coming from the outside, usually histidine. And any globin gene will bind to oxygen. So I said this is myoglobin. Myoglobin is a protein that's at very high concentrations in skeletal muscles. It has an oxygen storage role, and particularly in contexts where, like, a sperm whale. So a sperm whale has a very high myoglobin concentration in its in its muscles, and that allows it to effectively store oxygen and not breathe for a long period of time because its muscles have access to oxygen that's loaded up into the myoglobin in its muscles. So why doesn't it just do what myoglobin does? To start thinking about this, let's look at the binding of oxygen to myoglobin. I'm going to make myself go away. So what I'm showing here is a binding curve. We've got on the x-axis the concentration of oxygen. I'm writing this as a partial pressure because it's a dissolved gas, but a partial pressure is proportional to a concentration. So I'm going to treat them basically interchangeable and interchangeably for the purpose of this video. And then on this axis, we have the fractional saturation. What fraction of the molecules are bound, of the myoglobin molecules are bound to oxygen? We could write that as follows, that the fractional saturation here equals myoglobin free. I'm going to write this as MB alone versus myoglobin bound to oxygen molecules. This we've seen in a previous video is related. We can describe this in terms of the KD as follows. So what's the X that binds plus the KD? So in this case, X is going to be the partial pressure of oxygen. So how much oxygen is around? Again, with the sort of caveat that a partial pressure is that everything's going to be in partial pressure units, which are torr, not concentration like we normally talk about, say, molar. Okay. So this is a good chance to pause if you want to work on your biochemistry skills and ask, what is the KD for myoglobin binding based on this curve? So what is the oxygen binding KD for myoglobin? So if you want, you have a chance to pause the video. I'll let you look for the pause button. Cool. Let's talk about what the KD is. The KD is the point at which this curve reaches half saturation. So we're at 0.5 on the theta scale. And then we drop down and we ask, well, what is the concentration there? And it turns out, I didn't draw my lines very well, but this is about 30 torr. So it's about 30 torr because that's where, let's draw this better, where this curve crosses the concentration of oxygen, or in this case, the partial pressure of oxygen, where theta is 50%. All right, cool. Just to show this and make sure that we have this skill remembered, we can show the same data on a log axis. So here I'm showing partial pressure of oxygen. Here I'm showing the log of the partial pressure of oxygen. And the reason that we often do this is it lets us cover a larger range of scale, right? So here we're going 10 to the minus 1 to 10 to the minus 4, whereas here we're going from basically 0 to 100. So this is roughly 2 orders of magnitude. This is 1, 2, 3, 4, 5 orders of magnitude. But it does change the shape of the curve, right? So it goes from being this sort of what looks like a simple saturating curve, a hyperbolic curve, to something that looks more sigmoidal. But that's just because we changed the x-axis. And again, review, well, what's the KD? Well, we can figure that out the same way on this axis. So we go, okay, it's 50%. And then we ask, what does it hit here? And it turns out it hits the 10 to the, sorry, it's 3 times 10 to the 1, which is 30 torr. So we get the same KD whether we plot this on a log plot or a non-log plot. Okay, cool. All right, so now let's contrast myoglobin, which is our molecule that binds to 1 oxygen, with hemoglobin, our molecule that binds to 4 oxygens. So here again is myoglobin for reference. If we said, well, what's hemoglobin going to look like? First guess would be it's going to probably look the same-ish. But instead, we see something very different. And this has 2 different features. First, well, 3 different features. It takes, it's slower to bind. And I'm putting that in quotes because it's not really slower. This is time, but it takes more oxygen to get it to bind at all. But once it binds quicker, meaning that there is a steeper transition from being unbound to bound, which means that it saturates earlier, right? So for this myoglobin curve, we're still a long way from saturation. We have to keep going way out here for it to reach 100%. And hemoglobin is basically done by, say, 60 torr. So hemoglobin is behaving very differently than myoglobin. We can see the same thing on the log plot. That's why I set that up earlier, is what you can see is the curve is now much steeper, right? Whereas before we had this sort of shallow S-shaped curve, now it's getting much, much sharper, going from nothing bound to bound. All right. This is the example of cooperativity, where binding of a molecule at one site on a macromolecule affects the affinity of other sites for the same ligand. So you're seeing a cooperative transition here. So let's unpack what that means in some more detail. So first, let's do it functionally. What does this mean? So if you look in somebody's blood, the blood near their lungs has a level of about 100 torr. So this is the concentration of oxygen or the partial pressure of oxygen near your lungs. The partial pressure of oxygen near your muscle is around 30, so it's right around here. So how would these compare as delivery molecules, right? So my hemoglobin is a delivery molecule. Myoglobin isn't, but if we pretended it was a delivery molecule, how good would it be compared to hemoglobin? How would you even think about that? So maybe pause and think about that for a moment. How, would they be the same or different as delivery molecules for oxygen? All right, I'm assuming that you paused. The answer is that hemoglobin can drop off more oxygen. And the way we can think about this is using a delta theta. We can say, what is theta in the lungs versus in the muscle? And so for hemoglobin, this value is 1.0 minus 0.5, which means that 50% of the hemoglobin molecules dropped off their load, right? If we look at myoglobin, we see that it goes from, say, 0.7, right? That's what the fractional saturation is at 100 torr, down to 0.5. So about 20% of myoglobin molecules dropped off their load. And the way you might think about this is imagine a FedEx truck leaves the warehouse and drops off 20% of its load and then drives back to the warehouse. So it's going to be very inefficient. You're going to have to do multiple trips to move that whole warehouse because you're only unloading 20% of the cargo. Hemoglobin unloads 50% right here, so it's unloading 50% of its cargo every time. And there's some more complexities actually that I'm not going to get into in this video, but there's actually some pH effects and everything that can actually make it so it drops off even more. So it drops off more like 90% of its load. But even if it's only 50%, it's dropping off a larger fraction of its load every time around. So it's more efficient as a delivery molecule than myoglobin would be if it was a delivery molecule. Okay, so it's good to be cooperative because it has functional consequences. How is this achieved mechanistically? It turns out this is achieved because hemoglobin is in equilibrium between two different states, R and T. You can see that this is this fluctuation or this diagram that was made by Janet Iwasa. She's got some really nice animations of hemoglobin. So it's going back and forth between R and T. The R state has a higher oxygen affinity than the T state. So in this animation, we're seeing oxygen sitting down on the heme ring, and it's doing so when oxygen is in the R state. It's closer, it's got a better interaction with the iron than in the T state. It's a little bit further away. And further, this binding is linked to conformational change. And hopefully this makes sense, right? Because the oxygen binds more tightly to the R state than the T state. They have different structures. And so what that means is if oxygen's around, it's going to prefer the R form, that's red state, over the T state because it binds more tightly. That's for the same reason that the GPCRs will form the active state when there's the hormone around, right? In this case, if oxygen is around, it's going to shift the equilibrium to the R state. Okay. Finally, there is a transition between states that is all or none. So basically the molecule, all four of these subunits are either in R or in T, and these are driven together. So it's either all R or all T. And this is an approximation. There's some subtle differences that happen here, but it's a good starting point to understand how the systems work, to imagine that it really is going from all R to all T. This is enforced by actually physical interactions between the subunits. So each of these interactions, now this is sort of drawn as a surface, each of these surfaces has amino acids that are grinding against each other or interacting with each other, which basically makes it so that if you're in one form at one subunit, it drags the other form into it. And because this is a ring, basically the whole thing has to move as a subunit to keep those interactions satisfied. And I put this blank slide there to remind myself to actually go and show you this. A good physical example of an all or none system is one of these fortune tellers. So it can either be in R or it can be in T. It can be in R or it can be in T, but it is basically impossible to take a fortune teller and make it halfway between those states unless I open it up like this, and now it's no longer in this sort of state. But so this is hemoglobin, R, T, R, T. Okay. Cool. Sure, it does this thing. How does this lead to an S-shaped binding curve, right? That's what we really have to understand here. And so first, we have to set up some of the thermodynamics, and then we're going to look inside of a test tube and see what we see in a theoretical sense. So first thing to note is that hemoglobin favors the T state in the absence of oxygen. So this is the favored form of the receptor in the absence of oxygen. I'm just going to draw that as this sort of box shape, and I'm drawing the R shape as a circle, just to have some shapes to draw. What that means is if we were to say, look in a cell or your bloodstream or a test tube, what we would see is most of the molecules, most of the time, are in this T state. Now, occasionally you're flipping into R, right? Because this is a thermodynamic system, everything's bouncing around randomly. But on average, most of the time, these are all in this T form. All right, now let's imagine we're actually in the bloodstream. We get closer to the lungs. Our oxygen partial pressure starts to go up. We get more and more oxygen in the molecule shown in red. And then we get a magical event where oxygen binds to, say, this low affinity form or gets nearby or runs into it when it happens to already be in the T form, the R form. But now we have oxygen bound to a high affinity site on a hemoglobin, and there are 4 open sites that have high affinity that don't have anything in them. So what do? Well, look, there's already a bunch of oxygen around, right? And so that oxygen is going to load up into these high affinity sites. And so the system went from having no oxygen bound at any of the hemoglobins to now we just filled up an entire hemoglobin. It went from being nothing bound to 4 bound at 1. And let's imagine this continues. The oxygen partial pressure keeps going up, keeps going up. We have another event where oxygen binds to a T state, drives it into the R state, and now you've got exposed high affinity sites that suck in other ones, that suck in oxygens that are already around. And so that leads to that we get this early lag in T because in oxygen binding, because early on, the T state dominates, right? We're sort of waiting around for one of these R state forms to be populated. So we keep adding oxygen, nothing's binding. But then we happen to get to one of these bound states, and now the whole system loads up. So we got up to 20% bound right here, but still most of the system is in the R state. But as we add more and more and more oxygen, Le Chatelier's principle is saying, hey, we need to be in R. Like it's starting to shift us more and more towards R. So we get this very rapid transition, this sharp increase. So after this lag, suddenly we're going to the R form. And then finally we end up all loaded in the R form. And so the entire system goes from being in T to T with R, loaded R, to then completely loaded R. And that means if we look in solution, we basically only see two states. We see the unloaded T and we see the fully loaded R and nothing in between. And this is what we really mean by a cooperative system, right? This cooperatively went from T to fully loaded into R. Cooperative transition, T to R. I think I'm going to have things that I need to erase here. Okay, so actually let me erase what I just wrote. Sorry, got ahead of myself. Riffing. Okay, and so what did my past self want to say here? It wanted to say that the binding of the first oxygen stabilizes this R state, which exposes these surfaces, so it loads up the oxygen at those remaining sites. It exposes these high affinity sites that don't have oxygen around, so oxygen loads into them. And the analogy I like for this is it's actually a lot like an Uber. So imagine you are at a party with three of your roommates. You have three roommates, and you like each other, but you're not like the best friends in the world. And you all have to go home. And if Ubers were free, you'd all take your own ride, right? I mean, because then one of you could choose to listen to smooth jazz, and one of you could choose to listen to country. You all have all the options you want. But it turns out that Ubers are expensive, right? And so instead of all of you taking individual Ubers, you all ride together. You take a single Uber because that's way more cost effective than each of you taking your own. And so this is actually really what's happening in these chemical systems. As cooperativity arises because the binding the first site is expensive, so it has to pay to put it into that binding competent R state. But once it's there, everybody else rides for free. And so a system where there's a cost to loading the first site means that you get everybody else for free and you get cooperativity. Now, mathematically, we can model this with something called the Hill equation, and I don't want to derive it for the interest of time here, but what I'll just show it, and what this Hill equation has is it looks a lot like a normal binding model, right, where you've got these X's and these K's, but now we have this N on there. So X, I guess I'll say what these are. X is the concentration, KD is the dissociation constant, and then N is approximately the number of cooperating sites. So the higher you're in, the more cooperativity, the more cooperating sites are available. This is used not only to model this kind of cooperative system, but also all kinds of interesting cooperative systems in biochemistry. And so N is actually a sort of squishy number. It's not necessarily one site, two site, three sites. You see cooperativities of like 2.8. But again, to a first approximation, the way we can think about it is it's about the number of sites that are cooperating in the binding event. As you increase the N, you make a steeper binding curve. So here is N equals 1. Looks a heck of a lot like a myoglobin curve, and of course it does. I'm going to go back a slide. Because we're putting an N in, and if we have an N of 1, we just get back a normal binding model. But as we increase the N, as we make the N more higher and higher, we get steeper and steeper transitions. I think it's actually easier to see on the log plot side, right? So if we look at the log version of this, it gets steeper and steeper, eventually ending up almost as a step function where it's off and then now it's on. It's fully loaded in one quick transition. Okay, so that's cooperativity. If you've taken a biology class before, you probably encountered hemoglobin. So I wanted to also say other molecules do it. Hemoglobin is just such a good example. We always teach with it. But other molecules do it too, and I wanted to at least very briefly cover them. For example, immune receptors might do this. So this is a toll-like receptor that sits on the surface of immune cells. It recognizes lipopolysaccharides, this receptor, which is a chunk of bacterial outer membranes. And the only way that it can work is to assemble with two of these into downstream. Basically, this interior part assembles and then passes on the message to activate inflammation. This is a cooperative process, two sites working together to give rise to this inflammatory response. People have engineered cooperativity into enzymes. They've taken two enzymes that are inactive, that are basically two pieces of it. They built a protein scaffold that's whose assembly is controlled by the addition of a small molecule, and they can actually build a system that goes from being basically inactive to basically fully inactive just through the addition of a small molecule. So it's cooperatively engineered. And then finally, here's a really good example of an extreme form of cooperativity. So acetyl-CoA carboxylase is the enzyme that is the rate-limiting step in the control of fatty acid synthesis. Sorry, the synthesis of fatty acids. The way that it is regulated is actually through giant filament formation. So this subunit gets repeated and gets repeated and gets repeated and gets repeated. And this whole complex, when it assembles into this filament, is hyperactive through interactions between the subunits. So we're getting cooperativity at a large scale. It's not just, one going to two or two going to four. It's like multiple, tens of dimers that assemble into these long arrays that have cooperative activation. Okay, so pretty much done. I want to quickly summarize our key points. The first is that many biomolecules exhibit cooperativity where binding at one site allosterically alters the activity or the affinity at other sites for the same ligand. And the good way to think about this is the first binder pays to put the rest of the molecule into, first binder pays to put the rest of the sites into a high affinity state, then everybody else rides for free. Your friend pays for the Uber, so you ride their Uber, you don't ride somebody else's Uber. And mathematically, we can describe this using this Hill coefficient, where we've got this n term that we add to the normal binding model, which roughly describes the number of interacting sites. Okay, so that is what I have on allostery and cooperativity. Hope you enjoyed this set of videos. In future videos, we're going to start looking at things like enzymes and enzyme activity, so I look forward to seeing that with you, talking about that with you. But until then, have a great rest of your day, evening, morning. One of these days, I'll figure out how to end a video where I don't flub that. But anyway, see you later.